Hi everyone, welcome to the next session. In last class, we have discussed about the working stress method, as well as we have discussed about the what is meant by balanced section, what is meant by under reinforced section, and what is meant by over reinforced section. We have discussed. In this class, we are going to discussing about the limit state method of collapse under various type of conditions. From this onwards, totally we are discussing our design completely on limit state method of collapse. If you observe here, well, before going to the limit state method of collapse and serviceability and what is meant by limit state method, first we will discuss here. If you see here, limit state method is first classified into limit state method of collapse as well as limit state method of serviceability. Already we are discussing in our introduction part what is meant by limit state method of collapse and what is meant by limit state method of serviceability. Limit state method of collapse means while designing any structural member, due to this application of loads, the structural member will may get compression, flexure, shear and torsion. That means if you are after construction of the structure, due to application of the load, the member will experience these forces. Without getting those forces in the structural member, if you design the concrete member, that it will be called as a limit state under limit state method of collapse. Again, if you see the limit state method of serviceability, in limit state method of serviceability, we are designing the structural member for cracking, deflection and vibration. That means how much year you are designing the structural member, in that design life it should not show any deformation, deflection and cracking throughout its entire life. If you design the structure in such a way that it will be called as a limit state of serviceability. If you see here, limit state method of collapse under flexural condition, that means flexural condition means due to bending. Suppose I am taking this concrete member and I am applying the load. Due to this application of the load, the member will may bend. In bending condition, how the various type of forces coming on the structure we are discussing here. Under flexural condition, the member will may experience compression as well as it will may experience flexure, as well as it will may experience shear, as well as it will may experience torsion. If you take the columns will get the compressive forces. That means due to this axial loading condition, columns majorly will have the compression. Again, if you take the beam, for beam both compression and flexure you will may get experience. For shear also you will get for the beams, and the torsion also you will get for some structural member due to the equal and opposite forces. From this topic onwards we are discussing about the limit state method of collapse. And while going too deep into the discussion, first we will see the different types of assumptions for limit state method of collapse under flexural condition. Here I am writing it as under flexural condition. Under flexural condition. Limit state method of collapse under flexural condition. We are going to know deeply about the limit state method of collapse. We will see some of the assumptions given by the IS 456 code book. In this code book there are different types of assumptions. First one by one assumption we will discuss. Later we will go into the design of the structural members. If you see here, the first assumption is the plane section remains plane before and after bending. That means suppose here I am taking some simply supported rectangular beam. I am considering here as one section AB or XX, anything you can write is, and in this section I am applying some uniformly distributed load. Due to this loading condition, the beam member will may bend like this. That means if you observe here, due to this application of the uniformly distributed load, the beam will may bend in this direction. We will see in this next slide. If you see here, this is the same section. In this section I am applying some uniformly distributed load. Due to this uniformly distributed load, the member will may elongate in this direction, in this way. If you observe here, the middle portion, it will be called as a neutral axis, where neutral axis divides the member into compression phase as well as tension phase. Compression phase means concrete is strong in compression. That means concrete will not get failure above this portion. Concrete will get failure in this portion. That means tension phase concrete will may get failure. Hence why we are introducing the steel into the concrete to arrest that cracks. And if you see here, this is the same rectangular beam section, and I am introduced the some steel bar, and again I am applying the load. Due to this loading condition, you won't get any cracks in the bottom side of the steel. This concept already we are discussed in the introduction part. If you see here, this is the beam. In this beam I am showing by inserting the some steel bars. These steel bars are writing it as AST, that means area of the steel, where steel bars are introducing in the concrete member to gain the strength of the structure both in compression phase as well as tension phase. And again, if you see here in this diagram, the strain variation is linear. That means if you observe here, due to this loading condition, this section what you are getting, the section will may get transfer its position. That means this is the section, due to this application of the load, this section it won't get bent. That means strain is only variation, that is not bending. That means strain is in linear position. That means like this strain is varying. Okay, this is the section. Plane section remains plane, and after plane loading condition, before failure and after failure also same in the same direction. If you observe here, that means strain variation is linear. If you see here, this is the section. If you see here, this is the section before bending. After bending also, if you observe here, the strain diagram is in linear direction. That means it is not in any parabolic shape. The compression fiber of the particles may get shifted to the other position, but after shifting of these particles, the transfer zone of the member will not bending. That means strain variation is linear. The strain is changing from this point to this point, and from here to here. Again, after neutral axis, the strain again changing in the tension zone from this position to this position. In compression phase, it transferring into this direction, whereas in tension zone, the member will be transferring into in both of these directions. Okay, this is the how transferring strain variation is occurred in the section before bending and after bending. This is the first example of your plane section remains plane before and after bending. And the second one is the maximum compressive strain in concrete shall be taken as 0.0035 under flexural condition. We'll be going to discussing about this deeply. Now I'll explain about what is meant by stress and what is meant by strain. Stress already we know, stress is nothing but resisting force per unit area or load by area. Strain already we know, strain is nothing but change in length by original length. I am taking some concrete and I am preparing a concrete cube, concrete block, and I am testing it for a compression testing machine, and I am applying the load. Due to this application of the load, concrete will get strain. I am drawing the graph both for compression and strain. If you observe here, the first curve is the actual curve, it will be called, it is in parabolic shape. That means concrete, if you draw the stress and strain for concrete, the actual curve of the concrete, it will be in this parabolic shape. That means the first one is the parabolic shape, that is for actual concrete. If you introduce some steel into the concrete, again if you get the experimentation based on IS code book, these are the curves we are getting for the concrete experimentation. If you see here, the first one is having FCK. The first curve is called as a FCK, where FCK means characteristic compressive strength. Already we have discussed about the characteristic compressive strength. It is defined as the strength of the material below which not more than 5% of the test results are expected to fall. That means I am taking 100 cubes in 100 cubes, 95% of cubes will have to attain the maximum strength of the concrete. That means 95% of cubes will have to attain the maximum target strength. Only 5% of the test results are expected to fall. That means only 5% of the cubes may not give target strength also. That is no problem. That is the here characteristic strength we are getting from the concrete. And if you see here in this second diagram, in this second diagram we are introducing the one more time FCK divided by 1.15, that equal to 0.67 into FCK. Why we are introducing 1.5 means concrete what you are preparing in the site, it may have some limitations. That means the aggregates you are getting as well as the cement you are getting, as well as while mixing, the humidity conditions while mixing, while curing, all these parameters will not give the sufficient strength to the concrete in the same structural member for the design of a structure. While preparing the concrete for testing of cube, it will give the exact strength. FCK it will give for the exact strength. But while making this concrete to the same structural member, it does not give the exact value. Why? Because in laboratory testing, compression testing mission, FCK for characteristic strength, we are placing some steel bars at top and bottom of the cube. Due to this steel bars, concrete will get maximum, will give more strength. Whereas for designed structural members in a practical purpose, if you observe any beam or any slab column, we don't have any supporting members. Hence why concrete what you are testing in the compression testing mission, the same strength won't get in the practical field purpose. Hence why we are introducing the one term 1.5. If you observe here, where 0.67 into FCK. This is the compressive strength of the concrete for the structural member. If you take the concrete in structure, that strength it will be, we are taking it as 67% for the concrete structural member. In total characteristic strength, we are taking only 67%. And again, if you check the Throttle curve, in Throttle curve what we are doing means, we are introducing some factor of safety 1.5. According to code IS 456 2000, we are taking the factor of safety for concrete as 1.5. If I am taking this value 0.67 into FCK divided by 1.5, we will getting the value as 0.446 into FCK, where 0.446 into FCK is the design strength of the concrete member. That means the concrete what you are designing for any structural purpose, the structural member we are taking the strength of the concrete as 0.446 into FCK. Suppose if you are taking M20 grade, for M20 grade after construction of the structure, how much strength you are getting means, if you substitute the 0.446 into, for M20 grade we are having the FCK value as 20. 0.446 into 20 if you substitute, you will get the strength of the concrete member after construction. This is the diagrammatic representation how concrete we are attaining strength from the various type of experimental investigation. If you observe here from the stress strain diagram, the concrete is parabolic from origin to the strain of 0.002. If you observe here, from origin to 0.002, the graph is, the curve is parabolic. After that, from 0.002 to 0.0035, the curve is in linear position or in constant position. That means constant stress. Stress is constant, but strain is linearly varying. Why? Because due to the various type of conditions of the structural member. This is how we are calculating the maximum compressive strain in concrete shall be taken as 0.0035 under flexural condition, where 0.0035 is most important. Under flexural condition, the concrete in strain we are taking as 0.0035. Above the 0.0035, if you get the strain, the concrete cannot take care of any tensile loads, it will immediately fail you. And if you see the Throttle assumption, the Throttle assumption is the stress block is parabolic from neutral axis to the strain of 0.002 and rectangular up to the strain of 0.0035. Here this is the simply supported rectangular beam already we are discussed. In top portion we are having the compression phase, in bottom portion we are having the tangential zone. And if you observe here, from this top fiber to up to half of the depth of the steel bars we are considering the depth it will be called as a effective depth. And from assumption 2 we are having that maximum compressive strain in concrete we are taking it as 0.0035, as well as the tangential strength of the steel we are taking it as 0.002 plus 0.87 into Fy by Es, where Fy is the yield strength of the steel and Es is the modulus of elasticity of the steel. From this assumption, from this first assumption we are writing plane section remains plane, that means strain variation is linear. From second assumption, maximum compressive strain in concrete shall be taken as 0.0035 under flexible condition, as well as maximum tangential steel in steel we are taking as 0.002 plus 0.87 into Fy by Es. And if you observe here the throttle assumption, the stress block is parabolic from neutral axis to the strain of 0.002. This is our neutral axis. From neutral axis to strain of 0.002 is the stress block is parabolic. This is given by the IS code 456. Again, from 0.002 strain to the 0.0035 strain we are having the rectangular position. This assumption is from the throttle assumption. That means the stress block is parabolic from neutral axis to the strain of 0.002. From neutral axis to 0.002 the stress block is parabolic. Again, from 0.00 to 0.0035 the stress block is rectangular. If you observe here, where 0.36 into FCK BXU, this is the total compressive force acting on the rectangular beam. How this 0.36 into FCK BXU came, we will discuss in our next class. And if you observe here, this is the total tangential force. The total tangential force also we are taking that 0.87 into Fy into AST. This term also we will discuss in our later classes. If you observe here, the compression force is acting in this direction, the tangential force is acting in outward direction. Due to this both opposite actions, it forms a couple. Due to this couple, movement it will may happen. How much movement is happening and how the section we have to design based on the external loading condition, we will design the different types of structural members. Where these steel bars we are called as a area of the steel. The individual steel bars we are called it as area of steel rods. Up to this is the assumption, third assumption of IS 456. And next one we are having the tangential strength of the concrete is ignored. That means the concrete what you are introducing in the structural member below the tension zone also, it cannot take any type of loading condition. That means if you see here, this is our rectangular beam. In rectangular beam we are introducing the steel bars, and these steel bars bottom we are also placing the concrete. That means the concrete it won't any use. Why? Because it cannot take care of any load. You may ask the one question, why we are not introducing unnecessarily to the concrete below the tension zone? Why? Because the tangential strength of the concrete is ignored. We are not considering. Why? Because if you not introducing the concrete below the tension zone, the steel will may get exposed to the environment and it will may get corroded. Due to this corrosion, the structural member will may get failure. Hence why we are introducing the concrete in bottom zone also to give the bond between the steel and the concrete. If you provide concrete also, the tangential strength of the concrete below the tension zone we are not considering. Okay, next one is the fifth assumption. The fifth assumption is that the maximum tension. Ask the one question, why I am introducing here 0.87. If you observe here, factor of safety of concrete we are taking it as 1.5, whereas factor of safety of steel we are taking it as 1.15. From IS 456 we are taking it as factor of safety of concrete equal to 1.5, whereas factor of safety of steel we are taking it as 1.15. If you substitute the Fy divided by Es into 1.15, you will get this value as 0.87, and where 0.2 is the maximum strain occurring in the various type of structural member. If you take any mild steel or a HYST bars, high yield strength, in all type of these members will get strain of 0.2%. Up to this is the first assumption. The maximum tensile steel shall not exceed the strain of 0.002 plus 0.87 into Fy by Es. And next we are having some more assumptions. There is a good bond between the steel and concrete. This is also one type of assumptions for limit state of collapse under flexural condition. Up to this, these are the various type of assumptions for limit state of collapse under flexural condition. One by one I will explain very fastly. The first one is the plane section remains plane before and after bending. That means before bending also this section it will be like this, and after bending also this section it will be like this. That means this section won't bend, it will be like this. That means strain variation is linear. And the second one is the maximum compressive strain in concrete shall be taken as 0.0035. If you take the concrete beam and apply the load, due to this application of the load, the member will get strain. The strain which does not exceed 0.0035. That is the second assumption. And the third assumption is that the stress block is parabolic from neutral axis to the strain of 0.002 and rectangular up to the strain of 0.0035. Okay, and as well as the tensile strength of the concrete is ignored. That means the concrete what you are providing below the tension zone, it won't take care of any loads. Hence why tensile strength of the concrete we are ignoring below the zone of the tension. And whereas the maximum tensile steel shall not exceed 0.002 plus 0.87 into Fy by Es. Up to this, these are the various type of assumptions for limit state of collapse under flexural condition. In next class, we will discuss about the analysis of singly reinforced section and limiting depth of neutral axis. Thank you.